So we're going to look at differentiation from first principles. And when we differentiate, we know we can find the gradient of a tangent to a curve. And that a tangent to any function at a point is a straight line. And so we can try to find the gradient of this line at that point using one of our gradient formula. So we know that m equals y2 minus y1 over x2 minus x1, or there's other variations. You've got m equals v over h, or rise over run, or the change in y divided by the change in x. But to use any of those formula, we need 2 points on the line, and a tangent to a curve only touches at 1 point. So instead of a tangent, we can start by considering a chord, and the chord crosses the curve, and we have 2 points. But you can see in the picture on the screen that the gradient of the chord is not the same as the gradient of the tangent. The gradient of the chord is in black, and the gradient of the tangent's in red. And so we only have an approximation to the gradient of the tangent. So we can improve that approximation by changing the distance between our 2 points. So you can see at the moment they're 1 unit apart, and if I decrease the value of h, you can see that the gradient of my chord is now getting closer and closer to the gradient of my tangent. And mathematically, you can see that as I decrease h, so at 0.3 units away from each other, the gradient of my tangent I know is 1.51, but the gradient of my chord is going to be 1.81. And it gets closer and closer and closer to that magic 1.51 number on this picture. But when I actually get to 0, my gradient won't calculate because I can't divide by 0. So let's look at this from a mathematical standpoint. Right, so let's zoom in on that picture of this particular curve, and I'm going to mark 2 points. So I've got my gradient at my tangent drawn in, and I'm going to consider 2 points that are a distance of h apart. So this is going to be x, and this is going to be x plus h. So they're h units apart. And you can see I can work out the gradient of that chord between those 2 points. So the coordinates of the first point is going to be x, f of x. And the coordinates of my second point are going to be x plus h, f of x plus h. So now I can use my gradient formula to work out the gradient between those 2 points. So I know that m equals y2 minus y1 over x2 minus x1. And so I've got f of x plus h, take away f of x, divided by x plus h, take away x. And I can simplify that by collecting the like terms on the denominator to get f of x plus h minus f of x over h. But as I already discovered, I can't divide by 0. So if I want to have an instantaneous gradient, then I'm going to have to say that m equals, and as a limit h tends to 0, that my f of x plus h minus f of x all over h. And this is known as the differentiation from first principles. So f dash x, my gradient, equals at the limit as h tends to 0 of f of x plus h minus f of x all over h. So I'm going to look at an example now. I'm going to differentiate from first principles x squared. So the first thing I'm going to do is I'm going to write down my f dash x equals, now don't forget your limit, as h tends to 0, of f of x plus h minus f of x all over h. So I'm going to substitute in my curve f of x equals x squared. So I've got my limit, and I'm going to have x plus h all squared take away x squared all over h. Now the principle of this is that we want to be able to eliminate that h on the denominator. So I've got my limit, and I'm going to expand my bracket now. So I'm going to get x squared plus 2hx plus h squared take away x squared all over h. Now I'm going to get another colour, because x squared take away x squared is going to become 0. And so my limit becomes 2hx plus h squared over h. Now you can see I've got a common factor of h, which is going to allow me to cancel my denominator. So my limit, I've got h 2x plus h over h. So my h's will now cancel out. And so I'm left with 2x plus h, and I'm saying that my limit is h tending to 0, so I'm going to say that h is 0 now. And so that's going to give me 2x, which is what I would expect if I had differentiated f of x using my differentiation rules. So the next example we're going to look at is finding from first principles f dash x if f of x equals 4x plus 2x squared. So step 1, write down my differentiation from first principles. So f dash x equals the limit as h tends to 0 of f of x plus h minus f of x all over h. And again, I want to substitute in my 4x plus 2x squared. So I'm going to have my limit as h tends to 0, and I'm going to have 4 times x plus h plus 2 times x plus h all squared minus 4x plus 2x squared. And that's all going to be over h. Now I've put my 4x plus 2x squared in bracket because I'm having to take away the 4x and take away the 2x squared. So that gives me a limit as h tends to 0, and I'm going to expand everything out. So I'm going to get 4x plus 4h, and then I know that my x plus h squared gives me x squared plus 2hx plus h squared, so I'm going to be able to double all of that. So I've got 2x squared plus 4xh plus 2h squared, and I'm going to take away 4x, I'm going to take away 2x squared. And that's all over h. Now, my 4x take away 4x becomes 0, and my 2x squared take away 2x squared becomes 0. And so I'm left with my limit as h tends to 0 of 4h plus 4xh plus 2h squared. And that's all over h. So I need to take out my common factor of h. So my limit as h tends, if I wanted to, gives me 4 plus 4x plus 2h all over h. My h's will now cancel. So I'm left with my limit as h tends to 0 of 4 plus 4x plus 2h. And if I make h tend to 0, that 2h is going to become 0. So my final answer, and I'm going to write it with my x terms first, is going to be 4x plus 4. And if we go back to the original function, if I was differentiating that, then I would be expecting to get 4x plus 4 as my derivative. So the final example, we're going to find f dash x from first principles if f of x equals 2 over x. So again, first step, f dash x equals the limit of f of x plus h minus f of x all over h. So now we're going to substitute our function in. Now for this one, we've got a fraction on our denominator. Now I could write that as 2x to the negative 1, but that's not really going to help me. What I'm going to do, in fact, is I'm going to actually take that denominator out in front as a 1 over h. So that way I'm not having to have triple-decker fractions whilst I'm doing my working out. So I'm going to substitute in my function. So I'm going to do 2 over x plus h minus 2 over x. Now, I've still got an h on my denominator, so I need to use my kiss and smile technique to make my denominators the same so I can actually subtract those fractions. So I've got my limit as h tends to 0 of 1 over h, and I'm going to smile by multiplying my denominators, and then I'm going to do 2x minus 2x plus h. So my limit as h tends to 0 of 1 over h, I need to expand my bracket, so I've got 2x minus 2x minus 2h all over x squared plus hx. So my limit as h tends to 0 is 1 over h, and if I go back up here, 2x take away 2x becomes 0, so I'm going to end up with minus 2h over x squared plus hx. Now you can see I can cancel that h that's on the numerator and the denominator, and so that gives me my limit as h tends to 0 of minus 2 over x squared plus hx. And if I just move everything up a bit, if I let h equal 0, that's going to eliminate the plus hx, so I'm going to be left with minus 2 over x squared, which is what I would expect if I had made my function 2x to the negative 1, because I would have multiplied by negative 1 and lowered the power by 1, and I would have ended up with negative 2 to the x to the minus 2, and then using my rules of indices, I would have been able to make that positive by moving it to the denominator.